All right, welcome back. Today we're bringing you an explainer on a truly heavyweight computer science battle. We're looking at a classic algorithmic showdown here. Two absolute titans of computation going head-to-head in a maze-solving race. On one side, we have the legendary Dijkstra's algorithm, and on the other, the highly strategic A-star algorithm. So let's just get right into the arena.
But first, I want you to picture this. You're playing a real-time strategy game, maybe something like Age of Empires. You click on this massive army, you tell them to cross the entire map, and suddenly, they get stuck on a tree. Or, they take a wildly nonsensical detour right into an enemy base. Have you ever wondered how game characters actually navigate those massive grids? And why it's so unbelievably frustrating when they fail?
Okay, let's dive into this. Because pathfinding isn't just about stopping your video game units from blindly walking into walls. It's actually the invisible engine powering huge parts of our modern world. When Google Maps routes you around a massive traffic jam, or when an autonomous drone calculates the absolute most efficient delivery flight path, they're using pathfinding algorithms. At the end of the day, we're essentially trying to find the shortest possible path between 2 points on a highly complex grid. So here's our path to the checkered flag for today's explainer. We'll hit the universal pathfinding problem, generating the maze arena, the algorithmic heavyweights, the maze scaling race, crunching the runtime data, and finally, the ultimate winner.
Section 1. The universal pathfinding problem, when units get stuck.
You might be wondering, why does finding the absolute shortest path actually matter so much? Well, simply put, inefficiency equals lag. And lag equals a totally terrible user experience. As our source material directly points out, increasing the efficiency of the pathfinding algorithm used can aid in the better playability of the game by solving the existing problems. If players are constantly complaining about lag or units acting foolishly, it all traces back to the math under the hood. Better algorithms literally mean better games, cheaper drone flights, and way faster map routing.
Let's move to Section 2. Generating the maze arena. Building the grid. Now, to test these algorithms fairly, we can't just use one simple, basic maze. We need to procedurally generate them. Our arena is actually built using something called the recursive backtracker algorithm. It uses a depth-first search technique to literally carve out a maze, step by step. So it starts at a point, randomly smashes through a wall to an unvisited spot, and just keeps going. When it eventually gets trapped in a dead end, it simply backs up to the last spot with uncarved walls and starts again. It repeats the whole shebang until the entire grid is filled.
Just look at the visual on screen here. It perfectly captures that exact carving process in action. The red line acts kind of like a drill moving through the grid. What this generates is what computer scientists formally call a perfect maze. Now, a perfect maze has a very specific definition. It means there are no isolated nodes, absolutely no loops, and crucially, exactly one unique path between any 2 points.
And this brilliantly illustrates what a massive, complex, perfect maze actually looks like. But let's be real, real life and real video games aren't perfect mazes. You almost always have multiple ways to get to your destination, right? So, to make this a genuinely fair, real-world test, the researchers apply something called dead-end culling. They essentially knock down the walls on the dead ends to create what's known as a braided maze. This creates an arena with multiple possible paths of varying lengths.
Moving right along to Section 3. The algorithmic heavyweights. Introducing the contenders.
All right, the arena's built, the crowds are roaring. In the blue corner, we have Dijkstra's algorithm. This guy is the reliable workhorse. But here's the thing you gotta know. Dijkstra is exhaustive. It expands outwards in literally every single direction from the start node. Think of it like pouring a giant bucket of water onto a map. The water just spreads out perfectly evenly in a growing circle until it eventually floods the destination. It completely guarantees it will find the shortest path, but man, does it check a lot of useless ground to get there.
And in the red corner, A-star. Now, A-star is actually a modification of Dijkstra's, but with a truly massive upgrade. It uses a heuristic function. Basically, it acts like a strategic guided missile. Instead of searching equally in all directions, A-star uses an F-cost and an H-cost, which is essentially a mathematical compass, to estimate the distance to the end goal. It guesses the right direction and smartly prioritizes searching that way.
So the crucial point we need to take away here is the fundamental difference in their overall strategy. We've got Dijkstra relying on a totally exhaustive check-everything search versus A-star utilizing a heuristic, educated guess search. It's essentially brute force versus calculated intelligence.
If you direct your attention to the slide, notice how the blue path zeroes in beautifully on the target.
The colors represent the nodes it checks. Rather than wasting precious processing power expanding backward or sideways away from the goal, it creates this narrow, highly focused path directly toward the endpoint.
All right, Section 4, the maze scaling race. 40 by 40 to 320 by 320 grids. It's time to see how these algorithms actually perform under pressure, scaling from small 40 by 40 grids up to massive 320 by 320 behemoths. Now, I want to clarify one very important thing before we look at the results. Accuracy is not the debate here at all. Both algorithms are mathematically proven to find the exact same shortest path. They both succeed in the task. This showdown is purely a battle of runtime speed. The only question is, who does it faster? Section 5. Crunching the runtime data. The tail of the tape. The stopwatches have been clicked. Now, what's really interesting about this slide is the sheer scale of the numbers. Look at how aggressively both times increase as the grid size goes up. They both experience this massive exponential jump in the milliseconds required to solve the maze. At 40 by 40, they're lightning fast. But by the time we hit 320 by 320, they are crunching huge amounts of data. However, if you notice the right column, A-star manages to maintain a constant lead across the entire board. Just look at this number, 3.12. When we look at the 80 by 80 grid, A-star is over 3 times faster than Dijkstra. I mean, that is a massive performance gap. To put that into perspective, in a video game, that's literally the difference between a character moving instantly the second you click versus the entire game freezing up for half a second just to think. A-star completely dominates in these smaller to mid-sized arenas.
And finally, Section 6, the ultimate winner, the plot twist.
So based on those massive numbers, A-star's the undisputed champion, right? Well, yes, it absolutely wins the race every single time. But as researchers mapped out the ratio of Dijkstra's runtime compared to A-star, they noticed something completely fascinating hidden deep in the data. The ratio steadily drops. While A-star was over 3 times faster at 80 by 80, by the time they reached that massive 320 by 320 grid, A-star was only 1.5 times faster. Why? Because as the map gets incredibly large, A-star's heuristic function, that whole strategic guessing mechanism we talked about, really starts to struggle with its approximations. There are simply too many complex variables at play, and its massive speed advantage starts to vanish.
Which leaves us with a truly fascinating question. We know A-star is our current champion, for sure. But as modern games, real-world drone networks, and massive city grids scale to unimaginably huge sizes, will A-star still reign supreme? Or will its diminishing lead mean that computer science is going to need a brand new pathfinding champion for the giant grids of tomorrow? Thank you so much for exploring this data with us today, and keep questioning the tech that moves our world.